Welcome back, everyone. So it's a great honor for me today to present the results for the FetReg challenge. Here is a quick outline of our presentation from today. I'll be introducing the FetReg challenge, and then we'll have 2 to 3 minutes of participant presentation. And then the results for segmentation task will be presented by Alessandro, and the results for registration task will be presented by Francisco. The organizing team is shown over here, and I'm very excited to say that all the organizers are attending this event. So we'll be happy to take any questions at the end of this session. And we are very thankful to our sponsors, Medtronic, NVIDIA, and E4 Computing for supporting this challenge. So let's move on to the introduction of this challenge.
Hello, everyone. I welcome you all to the placental vessel segmentation and registration in Fetoscopy challenge presentation. This challenge is organized as part of the MICCAI endoscopic vision challenges. Let me introduce you to the FetReg organizing committee. I am Sofia Bano, and with me the co-organizers are Alessandro Casilla, Francisco Vasconcelos, Sara Muccia, and Daniel Slono. We are all part of one or more institutions listed in this slide. We are very excited to have the support from 3 major fetal medicine units from across Europe, and also from the GIFT Search project. And also, we are extremely thankful to our sponsors, Medtronic, NVIDIA, and E4 Computer Engineering, who supported this challenge. So let's move on to the context, clinical context of this challenge. Fetoscopy laser photocoagulation is a procedure which is used for the treatment of twin-to-twin transfusion syndrome. TTTS is a fetal anomaly that affects identical twins sharing a monoclonic placenta, where in TTTS, the flow of blood between the 2 fetuses becomes uneven. As a result, the donor experiences slow growth, while the recipient is at a risk of heart failure. So in order to treat this, fetoscopic laser photocoagulation is performed, in which the surgeon inserts the endoscope or fetoscope into the amniotic sac and localizes the interfetus membrane and use it as a guide for finding the abnormal connections. Once these abnormal connections are localized by the surgeon, these are then ablated with the help of a laser tool, and in order to disconnect the flow of blood or regulate the flow of blood between the 2 fetuses. This is a highly challenging procedure because the field of view is very limited in this procedure. Moreover, the visual conditions are very difficult, and they vary a lot from one patient to another patient. As you can see in these 3 examples, there are conditions such as poor visibility, low resolution, varying illumination, fluid turbidity, and also specular highlights and occlusion occurring in a fetoscopic scene all the time. And if I talk about challenges from creating or increasing the field of view of fetoscopy, these views are highly dynamic. And also, because this procedure is performed using a monocular camera, the ground truth transformations or registrations are not available for mosaicing. Nevertheless, we believe that computer-assisted techniques can improve this procedure and can guide the surgeons during this procedure to improve the surgical outcome. Therefore, we started looking into the task of fetoscopy registration. One of the major challenges in fetoscopy data is the interpatient and intrapatient variability. Moreover, fetoscopy videos captured at different clinical sites varies also in terms of the recording setup. Therefore, we started collecting large-scale multi-center fetoscope data from 3 major sites across Europe. These are University College London Hospital, Genena Slini Institution in Italy, and University Hospital Leuven in Belgium. Using this data, we come up with two tasks for this challenge, where the main aim was to design generalized algorithm for solving these two tasks. These two tasks are number one, the placental semantic segmentation, where we label the data for three classes, which are vessel, laser tool, and fetus presence. The second task was placental RGB frame registration for mosaicking, where a demo is shown over here, where the task was to compute the transformation or homographic transformation between adjacent frames and to create a mosaic from these transformations. The collected data set was then annotated to obtain the ground truth for the segmentation task. We were given guidelines from the clinician on the three labels that we wanted to annotate on each frame. The annotators followed these guidelines and annotated the data set. Then this data set was reviewed by two researchers, and if there was a need of improvement, this was flagged. And if there were some frames which were difficult or which were ambiguous to annotate, we went back to our clinician to verify our annotations. For the evaluation of segmentation tasks, since the ground truth was available, we can directly compare the predicted labels with the ground truth labels to evaluate or to quantitatively evaluate the performance of the segmentation model. We use a mean intersection over union as a measure over all test data for this purpose. But in terms of registration, since no ground truth is available because these videos are recorded in vivo setting and from a monocular camera, we looked into evaluating the consistency of the registration overlap. We used the metric that we presented in our last year's MICCAI paper for the purpose of quantitatively evaluating the registration. The registration evaluation is based on the assumption that adjacent frames will still have overlaps within a window of n consecutive frames. So let me quickly go through this registration evaluation process. So given the test clip, which is of n frames duration, the submitted registration algorithm computes the homography between the adjacent frames, which are represented over here. Then using these homography, we wrap frame 0 onto frame n, and then compute the overlap between these two frames. And then in the overlapping region, we compute the structure similarity index. The mean and median over the structure similarity index is then used as the evaluation metric. Now let's go through the training data set that we released. For the segmentation task, we released 2,060 images with pixel-wise annotations from 18 Fetoscopic videos. These images were labeled for vessel, laser tool, and fetus classes. Here you can see the bar plot showing the occurrences of each class per frame, and also the average number of pixels present per class per frame. From these plots, what we can observe is that there is the data set is highly imbalanced in terms of the three classes that we are interested in. For the task of registration, again, we released short video clips from these 18 Fetoscopy videos. In total, we released about more than 7,000 frames, but then these frames were not annotated for vessels, or they did not have any ground truth available for the registration task. In terms of the testing data set, this data set was not released to the participants, but it contains 6 in vivo Fetoscopy videos, about 658 images with pixel-wise annotations. Again, we see the same trend of class imbalance in this data set as well. And talking about the data set for the registration task, it contains 6 short clips from the same videos and more than 2,000 frames, unannotated frames. The evaluation for the registration task was performed on a subsequence of 200 frames from each video clip, such that this subsequence was free of occlusions, or the view in the subsequence was relatively planar or had some vessels clearly visible. In terms of the challenge setup, we released the training data for task 1 in early May and the training data for task 2 at the end of May. We also released a dataset description paper on arXiv, where we also presented the baseline result on the training dataset. We launched a Slack channel to support the participants, and the submissions were open from 20th of August until the 17th of September. We received 33 challenge registration and dataset access requests from participants of 16 different countries. And when we opened the team registration deadline, in total, 13 teams registered with a total of 22 team members from 11 different countries. And when the challenge closed, in total, we received submission from 7 teams for task 1, in total 16 team members, and these were from 9 different countries. For the task 2, we only received 1 submission. Let's quickly talk about the Docker submission setup. As I mentioned before, the test dataset was not released to the participant. The submission was through Synapse platform. We provided the participants with Docker examples for both tasks, and also we provided them with submission guidelines, and we set up a Slack support forum where they can easily approach us for any queries. Each participating team submitted their Docker through the Synapse platform on the FetReg project. And these Dockers were then verified for the validity of their output structure. If a Docker was invalid, the participating team was notified with the error so that they can update their Docker and resubmit it. And even in the case if it passed the test, the participating team was notified. Only the latest submitted Docker from a team were considered for the evaluation. In total, 7 teams submitted to the FetReg challenge. These teams are Team AQ led by Abdul Qayyum, Team Biomedical led by Chiara Lena, Team Krichet led by Daria Krichenova, Team OOF led by Jing Zhao, Team Rishab IITB led by Rishab Kanawal, Team RREB led by Vinod Patarai, and Team Sano led by Simon Tulatka. Here, I would like to highlight that Team Sano was the only team that submitted to both tasks. Although not competing, but in the evaluation, we also included our baseline method to make this comparison more interesting. So now let's move on to the participating team's presentations.
Hello, I am Abdul Qayyum and currently working as a postdoc researcher at National Engineering School in Brest, France. I am team member in this challenge, and here are the other members. I am presenting automatic placental vessel segmentation using recursive density unit based deep learning model. Our proposed approach is based on encoder and decoder technique. We have developed 2D densely based convolutional layers from scratch at encoder side without using any pre-trained weights. The number of dense layers used recursively with different convolutional layer data increases at each encoder block with feature reuse capability. The efficient and lightweight 2D convolutional layer block with 2D upsampling layer have been built on the decoder side of the proposed approach. The proposed dense block uses successive number of feature maps in each encoder layer. We have trained our proposed model using 5 k-fold cross-validation method and ensemble the output of each trained model using max majority voting ensemble method to combine or aggregate the final prediction segmentation map. We also use some test time augmentation method before ensembling and that is produced a little better performance. The flipping and rotation with different angles used as a test time augmentation that produce better performance. With the test time augmentation and ensembling, the prediction of uh, each cross-validation method with different training and validation samples, the proposed approach may provide the better and optimal solution for this semantic segmentation. We have used different hyperparameters for training and optimization of our proposed model. Here is the simple number of parameters. We have trained our proposed model using PyTorch and also use some other specific dependency for the data pre-processing and post-processing. We use different batch size, import sample, number of epochs, and Adam optimizer. The training time was 2.5 hours for the single train model. The code is publicly available at this link. Thank you so much for your listening.
We are Jessica Biagioli, Ilaria Anita Cintorrino, Gaia Romana De Paulis, and Chiara Lena, Master Thesis students in Biomedical Engineering from Politecnico di Milano, and the name of our team is Biopolymy Team. This is our work for Task 1 of Fetoscopic Placental Vessel Segmentation and Registration Challenge, where a large-scale multi-center dataset for semantic segmentation and video mosaicking algorithms in fetal environment was presented. In this work, we provide a new framework for the first task of this challenge, which is based on the combination of features extracted with histogram of oriented gradients and deep learning methods. Histogram of oriented gradients is a method to characterize object shape and appearance by the distribution of local intensity gradients or edge directions. This method can be applied to different architectures. After implementing different models, the best performances were reached with ResNet 50 as backbone, which is based on deep residual learning. The fully connected layers in the classifier are replaced by convolutional layers in order to output a heat map. The proposed histogram of oriented gradients vector injection is applied in the study at latent space level, but it could be embedded at different layers of the network. We performed 6-fold cross-validation to assess the robustness of the model. With the introduction of histogram of oriented gradients injection technique, the model is accurate in recognizing tool and fetus classes that are just present in the 28% of images. It provides also robust identification of vessels, even in case of branches or thin structures. On the right, there is a demonstration of our model applied to a brief intraoperative fetoscopic video. Despite poor image quality, our method is able to correctly segment vessels.
Hello, my name is Daria Krecheshnikova. I'm from Moscow State University, Department of Physics. Here is my solution. At first, I removed duplicated images from data. Then I performed multi-label stratified split into train, validation, and test paths to balance the class representatives. Then I augment train dataset using flips, rotation, and transposing. I train one separate model for each class. The best results gives UNet with series next 50 backbone. As loss function, I used combo loss. This is combination of dice loss, binary cross entropy, and focal loss. For optimization, I took Adam. I performed two-stage training. For the first 20 epochs, I used relatively large learning rate. Then I reduced it and used uneven schedule with restart. and repeat this until best convergence. On the last layer, I used sigmoid activation function to output sigmoid masks. Then I performed post-processing of the obtained masks. I count the number of pixels with a high probability, with a high confidence. And if this number were lower than some threshold, I output just 0 mask. In another case, I convert sigmoid mask to the binary mask. Then I took all binary masks from each model and concatenate them to make final prediction. This is it. Thank you for your attention and bye.
Hello, we are team overfitting. My name is Bai Bizhe and I have 2 teammates. I'm a new college graduate with Bachelor of Science from University of Toronto. My teammate Jiao Jing is a PhD candidate of Biomedical Engineering in Fudan University. My teammate Yan Qiao is a researcher in microport robotics. There are 3 parts in our algorithm, which are data pre-processing, data augmentation, and the main segmentation architecture. First of all, there are 3 major drawbacks we noticed of the FetReg dataset. The first one is some extreme lighting conditions, and the second one is all pictures are noisy, and the last one is the imbalance among classes. More specifically, there are around 2,000 occurrence of vessels and 600 occurrence of tools and 300 occurrence of feathers. We try to solve the noisiness and extreme lighting by contrast limited adaptive histogram equalization, or CLAHE, and medium blur. Then we try to solve the imbalance by data augmentation. This is the original image, and the red one is the image after our pre-processing. We could observe that the vessel is more obvious than the original image, and this would benefit neural network to capture features. The segmentation architecture we choose is UNet++ because it is mainstream in medical image segmentation, and the backbone we choose is EfficientNet. We choose EfficientNet because consideration of balance between speed and accuracy. The comparison between our algorithm and the baseline algorithm is shown at here. The left picture shows the IOU result among different folds and classes of our algorithm without the data augmentation and the pre-processing. We could observe the mean IOU is better than the baseline method by at least 4%. And the right image is the IOU result of our algorithm. We could observe the mean IOU of our method is at least 10% better than baseline. And thanks for your watching.
All. I am Rishabh Kantwal from India. I work on creating machine learning solutions. My passion is to help research groups and companies automate their work. I am 19-year-old. I am currently pursuing a dual degree program at Indian Institute of Technology, Bombay. I am currently in 4th year doing bachelor's in mechanical engineering and master's in machine intelligence and data science. I have taken part in this competition as a part of my research internship at Hiroshima University under International Linkage Degree Program. I found my interest in machine learning in my first year of study. Until now, I have worked on several projects. I have built models for various tasks for labs and companies. This involves model for target detection from drones, model for leaf tip counting for Agriculture Department of India. I also worked on disease classification, where I developed a state-of-the-art model for COVID-19 detection using chest CT ray scan images. This project motivated me to build computer vision applications for biomedical engineering. Now, I will briefly tell about the methodology that I used in this competition. There were 2060 images in this dataset with 4 classes. After analyzing the data, I knew that I would need image pre-processing before passing images to model. I used contrast limited adapted histogram equalization, which made images more clear. As you can see, after resizing, our pre-processed image was ready. We then pass this image to the UNet model with ResNet 101 as backbone, which predicts the mask. We then compute the loss function across the ground truth and the prediction. We validate our pre-processing by training images with and without applying histogram equalization. And as we can notice, the IOU has increased from 0.699 to 0.746 after applying CLAHE. We also analyzed different architectures, performance including PSPNet, LinkNet, UNet, and feature pyramid network. Among this, UNet achieved the highest IOU among 3 out of 4 classes and got highest IOU among these models. We then analyzed different backbones for UNet. This involved VGG19, MobileNet V2, ResNet 34, ResNet 101, Inception V3, and CNet 154. Among this, CNet 154 achieved highest IOU among classes 0, classes 1, and class 2 and got highest mean IOU. At last, I want to thank to the competition organizers, MICCAI, and my professor to giving me chance to participate in this competition. Other than model building, I learned about data handling and fine-tuning in this competition. For any query about the work, you can reach out me by mail at rishabhantwal11@gmail.com. Thank you.
Hello everyone, this is Ronak Subedi from Nami, Nepal, representing Team RREB in this EndoVis FetReg 2021 challenge, and welcome to this presentation. Introducing my team members, we have Revati Raman Goire from Nami, Nepal, Dr. Edward Vasquez from Relay Technology, London, and Dr. Vinod Bhattrai from UCL, London. Now I will talk briefly about the methods that we implemented for placental segmentation tasks. We started with U2Net as a base network, and then to fully leverage the effectiveness of joint objectives of complementary task annotations, we propose to compute the histogram of oriented gradients HOGs as annotations of pretext tasks and minimize the loss along with the semantic map annotations. HOGs are carefully designed handcrafted features for object detection. We add a separate law-enabled CNN network on the decoder part of the U2Net to regress the HOG features of the input image as shown in the figure alongside. The output from each decoder block is fed into the HOG regressor, which learns the parameter to predict the HOG correctly. We jointly minimize mean square error for loss of HOG features and cross entropy loss for semantic segmentation. Here is the qualitative comparison of our results with that of other methods. Thank you.
Hi, we are Sano Team from Sano Center for Computational Medicine from beautiful Krakow in Poland. My name is Szymon Płotka, and together with Aneta Lisowska and Arkadiusz Sitek, we would like to show you our solution for placental vessel segmentation and RGB frame registration for mosaicking. For placental vessel segmentation, we adopt an open-source feature pyramid network as a base neural network. As a backbone, we use well-known ResNet 152 with pre-trained weights. We use 6-fold cross-validation with a batch size of 4 and 100 epochs per fold. We use an Adam optimizer with an initial learning rate and weight decay of 10 to power minus 4. We use reduced learning rate by a factor of 0.1 when a metric stopped improving. As a loss function, we use cross-entropy loss. For training, we scale images and masks to 448 by 448 pixels and use a set of augmentations. For placental vessel registration and RGB frame registration for mosaicking, we propose an algorithm that uses the raw output from the segmentation algorithm of the channel corresponding to the placental vessel and the original RGB images. The only translation is modeled with the precision of 1 pixel. If frames are indexed by I is equal 1 to t, the algorithm finds t minus 1 translations between neighboring frames. On the left, you can see an example of RGB frame registration, and on the right, placental vessel registration. On the bottom, you can see the final results. Please note that we are the only team that solved this task. Thank you for your attention.
Now I hand over to Alessandro, who will present the results for task 1.
Thank you, Sofia. Now we will have a further look to the evaluation results for task 1, analyzing some sample results from the test set. This first frame is characterized by the presence of multiple blood vessels. We can see that most of the team segmented the vessel only with minor inaccuracies. For example, Team 2 have some pixels incorrectly classified as a tool. The small vessel bifurcation in the lower part of the frame was not accurately segmented by Teams 3 and 4. The highlighted crossing vessel in the right part of the frame was not fully segmented by most of the teams. In this frame from video 5, the red halo from the laser fiber pointer could hamper the segmentation performance. In fact, most of the teams segmented only partially the vessel, and this is probably due to the strong specularity on its surface. Teams 2 and 5, however, seems that are not affected by this issue. Instead, Team 3 identified the presence of a fetal part, probably due to the presence of the strong illumination by the red light. In this frame from video 1, we have a low illumination and multiple fetal parts. All the proposed method correctly identify the vessel and the upper left fetal part. That is incomplete in the Team 6. However, Team 6 and 1 segmented correctly the lower right fetal part that is incomplete in Teams 2 and 4. It's interesting to notice that some of the teams identified the shadow of the fetal part, highlighted by the white arrow, as a vessel. In this frame from video 4, most of the team segmented correctly the most visible vessel. The less visible one, highlighted, due to the low contrast and the low illumination, was fully segmented only by Team 6, and partially by the others. In this frame, it's also interesting to notice how the strong reflection on the tooltip led some of the teams to classify it as a fetal part. In this frame, most of the teams segmented correctly the tool and the most clear vessel in the center of the frame. The smallest vessel, indicated by the arrow, was missed by most of the teams. Teams 1 and 5 additionally predicted a null due to the presence of an inner reflection in the center vessel, while some of the other methods classify the underlying shadow as a vessel. In this frame from video 6, we have all the classes together and multiple issues. Some parts of the vessel are not very well contrasted. The tooltip is bright due to the reflection of the Fetoscope light. In particular, some models are confused by the presence of the small shadow in the tool, leading to the detection of the whitish part as a fetus. Team 2 and 5 segmented this image correctly. This is a summary of the results for task 1. The table on the left shows the leaderboard considering the overall mean intersection over union. The first three positions are the Team 2, Team 5, and Team 3. Team 2 won on 4 videos, and Team 5 on 2 videos. The box plot at the top left gives an idea of the performance of the team on each video. The bottom box plot summarizes the performance per class of each team. For time reason, I can't go into details here, but it's worth noticing the high performance variability on each video and per each class. This can be further noticed in the rank stability. Except for Team 8, all teams' ranking was switching depending on the video. Team 7 ranking switched only for one video. T1 ranking was stable and switched only 2 times with T5 ranking. This highlights that since this video is varying because there is a high variability in the Fetoscopic videos, the submitted methods are not able to generalize and can't tackle all the types of variabilities of this kind of data. Now I leave the floor to Francisco, who will present you the evaluation results for Task 2.
Thank you, Alessandro. And before we present the registration results, let's remind what's the logic behind our registration metric. What we're trying to accomplish is to measure the consistency across different frames between different registrations. So the different teams perform pairwise registration between different frames. And if we accumulate these registrations through consecutive frames, we will observe a drifting error. And we can measure this drifting error by comparing the warping of a moving image against its overlapping part in the source image. And we compare the structural similarity within this region. If we do this for the entire video and for all the videos across different distances of frames between 1 to 4, we arrive at our metric for this challenge. If we look at results from video 1 and video 2, we see that the different teams have different strategies to perform registration. While Team 1 favors a translation registration with very few degrees of freedom, Team 2 performs an affine registration with more degrees of freedom. This means that Team 2 is able to deal with perspective warpings, while Team 1 is not able to deal with any perspective changes, and sometimes overestimates translation to compensate for this fact. This is what we see in video 1 in the beginning at the left. And this is the reason why also in the structural similarity metric represented on the right, Team 1 has lower values in the beginning. On video 2, it's more challenging to both algorithms, but still Team 2 performs better overall. Video 3 represents an interesting case of an anterior placenta. In this case, the placenta surface is not frontoparallel to the camera. So there is a big perspective warping across different frames. Team 1 is not able to model this through a simple translation. While Team 2 is able to model this type of warpings, it still performs somewhat poorly due to lack of features for registration. On video 4, however, Team 1 performs better, especially in regions where vessels are not clearly visible, and Team 2 completely fails, producing a very large drift. And this is the trade-off between using less or more degrees of freedom. Errors with an affine registration will produce more erroneous warpings than simple errors in translation. The same happens in video 5 and video 6. These represent challenging videos where in some frames there are no clear distinguishable structure like the vessels. In this case, Team 2 fails to perform registration, and this results in huge warping errors. These errors are not present in Team 1 because they're simply using a translation registration. Overall, both teams perform very similarly in terms of average and median structural similarity index across all frames of all videos, with one team being better on 3 videos and the other team being better on the other 3. Team 2 just very marginally beats Team 1. And this represents exactly the trade-off between more degrees of freedom or less degrees of freedom in how we choose to perform the registration. So more challenging videos where in some frames there are not enough features and the tracking fails, Team 2 produces much larger errors that completely destroy the subsequent mosaic. However, when there are different perspective warpings across the video, Team 1 is not able to model that successively. And in this case, Team 1 is worse than Team 2. And with this, we now move on to the live session where we're going to present the awards.
So now we are going to present the awards in this live session. Before we move on to announcing who is the winner, I would like to remind that there should be a survey in the chat posted by Anika on the EndoVis challenge, journal challenge, and also on the FetReg challenge. So please do participate in those surveys. And so for the task 1, which was the segmentation task, we have 2 awards. One is $2,000 for the winner, and for the runner-up we have $1,500 award. We are very thankful to our sponsors, Medtronic and E4 Computer Engineering, for sponsoring these awards. And we are also very thankful to NVIDIA for supporting the FetReg challenge and providing us the platform for performing the evaluation. So let's see who are the winners. So Team 1, let me remind that these rankings were, the overall ranking were achieved based on the overall mean IOU value over all the 6 videos, annotated, segmentation annotated frames from 6 videos. So Team 1 is the top ranked team. Let's see who is Team 1 or who is the winner. So apparently Team 2 is the baseline team, which is not competing, so it's not getting any awards. So yeah, it's a bit disappointing for us. But yeah, let's now move on to the real winners and reveal Team 5. So the winning team for the task 1 segmentation is Team RREB, led by Vinod Bhattarai from UCL, with colleagues Rabati and Runast from NAMI institution in Nepal, and then Edward from Revat Technology UK. So congratulations team RREB on winning this first position award of $2,000 sponsored by Medtronic and E4 Computing. Congratulations. Moving on to the second or runner-up award, let me reveal who is Team 3. Shall we do that? Okay, let's go. It's Team Griched, led by Daria Grichenova from the Department of Physics, Moscow State University, Russia. Big congratulations to Daria for winning this runners-up award of $1,500. So congratulations to both the winners, winning team and the runner-up team. And let's reveal the names for the remaining teams. So here we are. I think it was a bit close competition towards the runner-up award, but yeah, clearly we have winners over here. So let's move on to the awards for registration. But before we move on to those awards, let me remind that there was only one team who was submitting to this challenge. So we named this award as the Brave Submission Award, considering the fact that there was only one team who was brave enough to submit to the registration task of Fetoscopy Mosaicking. So this award is for $1,500, sponsored by Medtronic and E4 Computing. We are very thankful to our sponsors once again for providing us the funds for these awards. So let's reveal the ranking. Of course, the award definitely goes to Team Sano, but let's see the rankings as well. So yeah, so the Brave Award winner team is Sano, led by Simon Polatka from Warsaw University of Technology with colleagues Anita and Arandes, again from the same institution. So congratulations, Team Sano. And I would like to mention here that here we were making a comparison of Sano versus Bano, the baseline method. And yeah, as Francisco mentioned, there were some cases where Team Sano was better, while there were some cases where baseline was better, or in some algorithms based on the challenges in each of the sequences. So with this, we come to the end of the awards. Once again, I congratulate all the winners, and I also congratulate all the participants for contributing to this challenge. So to wrap up, in terms of challenge experience, as organizers, all of us really enjoyed organizing this event, right from the beginning, from challenge design, dataset annotation, setting up the infrastructure, and much more. And I'm very thankful to my co-organizers for this challenge as well, because we were all very keen and involved in this organization. And in terms of the outcomes, placental semantic segmentation is still far from being solved. We have submissions with some interesting approaches, though we saw that these methods, they tend to work on some algorithms, but they don't tend to give as good performance as they should give on the other sequences. So clearly, either the data set of 18 annotated videos in this Fetoscopy domain is not enough, considering the variability in this data set, or we need to improve the algorithm that we are coming up with. In terms of registration tasks, it is even more far from being solved. And this probably is based on the fact that there are even more challenges in Fetoscopy video when it comes to the registration. And Francisco highlighted some of them in the analysis part. But the big question remains why there were more submissions for the segmentation task and not for the registration task. In our opinion, this was because of the fact that there is a lot of material and repositories available now for the segmentation task. But when it comes to Fetoscopy video registration, even the off-the-shelf algorithms or even their handcrafted features, they don't tend to work on these videos. So it becomes a bit challenging to design an algorithm for these registration tasks in Fetoscopy. And then what's next? We are preparing the challenge paper, and we anticipate it to be ready in next 6 to 8 months. We are looking into performing even more in-depth analysis of the segmentation models that were submitted, and then using these segmentation models for a vessel-based registration as well. So we have the reports from the participants, but we will be contacting them again to contribute to this journal paper as well. And also, I would like to mention that we will keep the submission system open for 1 more month, especially for the teams whose models were not well optimized, or they did not perform very well, so that they can fix their bugs and can resubmit a Docker with a bit better performance. So with this, I conclude my presentation. I would like to thank all my co-organizers and also EndoVis co-organizers for organizing this great event. And once again, I would like to thank our sponsors, Medtronic, NVIDIA, and E4 Computer Engineering for sponsoring the FetReg event. Thank you.